So consider a charge here, and that plus Q charge is shown here, positive charge, and we know around that charge there is electric field. The yellow lines represent the electric field lines, and we know they are perpendicular to the surfaces, and we have studied the electric field due to this charge at a distance r1, 1 by 4 pi epsilon 0 q by r square. That is the electric field. But potential equation is different. It is 1 by potential at the same distance. What is the potential? 1 by 5 epsilon 0 q by r only, no r square. Electric field it is 1 by 4 pi epsilon 0 q by r square. But potential 1 by 4 pi epsilon 0 q by r. Understood the difference? Adilashmi, what is the potential? Adilashmi, what is the potential at a distance r1? R1, what is the potential?
1 by 4 pi epsilon.
Q by?
R.
Q by R. Okay, electric field equation? Electric field equation tell? Potential 1 by 4 pi epsilon 0 Q by R. What is the equation for electric field at the same place, at the same distance? Abhinav, what is the equation for electric field at the same distance? Abhinav? Adityan, what is the electric field at the same distance? കണ്ടോ ഞാൻ പറഞ്ഞില്ലേ ഒരിക്കൽ പോലും ഉണ്ടാവില്ലേ ഈ പറഞ്ഞ ആദിത്യം പറയും വാട്ട് ഈസ് ദി ഇലക്ട്രിക് ഫീൽഡ് രക്ഷയില്ല ആദിത്യ ടെൽ ആദിത്യ വാട്ട് ഈസ് ദി ഇലക്ട്രിക് ഫീൽഡ് അറ്റ് എ ഡിസ്റ്റൻസ് ആർ ഫ്രം എ പോയിന്റ് ചാർജ് ആദിത്യ എവിടെ പോയി നിത്യം പറയുന്നില്ല സ്പീക്കിംഗ് പക്ഷെ കേൾക്കണില്ല മ്യൂട്ടായിരിക്കും കേൾക്കണില്ല കേട്ടോ
ഹലോ ടീച്ചർ
വാട്ട് ഈസ് ദി ഇലക്ട്രിക് ഫീൽഡ് അറ്റ് എ ഡിസ്റ്റൻസ് ആർ ഫ്രം എ ചാർജ് ഫോർമുല ടെൽ ഇലക്ട്രിക് ഫീൽഡ് അറ്റ് എ ഡിസ്റ്റൻസ് ആർ ഫ്രം എ ചാർജ് കേൾക്കണില്ല അക്ഷയ ടെൽ അക്ഷയ
Yes, teacher. 1 by 4 pi epsilon 0 q by r square.
ഓക്കെ ഇലക്ട്രിക് ഫീൽഡ് വരുമ്പോൾ q by r സ്ക്വയർ ആയിരിക്കും പൊട്ടൻഷ്യൽ വരുമ്പോൾ q by r അത്രേ ഉള്ളൂ കേട്ടോ അതാണ് അതിൻ്റെ ഡിഫറൻസ് ഓക്കെ സോ ഹിയർ യു ക്യാൻ സി വി ആർ സ്റ്റഡിങ് അബൌട്ട് ഇക്വിപൊട്ടൻഷ്യൽ സർഫസസ് സോ അറ്റ് ദ സെയിം ഡിസ്റ്റൻസ് ഫ്രം ദ ചാർജ് ഫോർ എക്സാമ്പിൾ ഇഫ് റേഡിയസ് ഈസ് r you can draw a sphere with that radius. You can draw a sphere. All points on that sphere, electric potential is same because 1 by 4 pi epsilon 0 q by r, r is not changing. So potential at every point on that surface will be same. Such a surface is known as equipotential surface. So here they have marked it as 10 volt. For example, first one is 10 volt. Then they have drawn another equipotential surface with another radius. As the radius increases, potential, what happens, children? Potential, as the radius increases, inversely proportional to distance. Decreases. So potential decreases, and we see first one was 10 volt, next one it is 9 volt. Potential decreased. As the distance increased, potential decreased. Understand? So, and another potential equipotential surface is drawn with a greater radius, and it is 8 volt potential. You see some difference here. Here 10 to 9, the difference between them, distance between them is very small. They are very close each other. Even though potential difference is 1 volt, they are very close here. But here 9 to 8, you know, as the distance increases, see, that difference, that means they are not close, they are far apart. Here see 7 volt, again distance increased. What is the meaning of that, children? Decrease in potential. See, decrease in potential. As the as it is far and far from the charge. It has to move a longer distance. It has to move a longer distance. That means to decrease the potential. For example, gravitational potential energy example I will tell. That means when it is taken to in higher and higher places, when a body is taken to higher and higher places, potential energy is increasing, isn't it? That is, we are taking it against the gravitational field. We are taking the body against the gravitational field. So, potential energy of the body increases. Here, against the gravitational field means you have to bring the charge towards it. Electric field is here, outwards. Electric field is outwards. We are bringing the charge towards it. So, the field lines are very close. What is the meaning? The electric field is very strong. If the field lines are very close, what is the meaning? Very strong electric field. Very strong electric field it is, with the field lines are close. Then also equipotential surface also, if they are close together, you can say the field is strong in that region. As we move far and far apart, the electric field decreases. As we move far from the charge, electric field is decreasing. So this equipotential surface also will be separated by a large distance. More distance. We see now here the field is electric field is weak in this region compared to the nearby region. This is far region, near region. So here the electric potential is very, very less. Understand? So the equipotential surfaces are close here. There the field is strong. And also one more thing, that they are perpendicular to each other. Electric equipotential surface and the field lines are perpendicular to each other. How will you prove that it is perpendicular? So that with the calculation equations on, we can show that. I will show with equation. Work done to take a charge on an equipotential. Can you tell children what is the work done to take a charge on an equipotential surface? Work done. Potential is same. There is no potential difference on an equipotential surface. What is the work done to take a charge from one point to the other? Work done to take a charge from one point to the other. Unit positive charge from one point to the other. What is it actually? What is it? Work done to take a unit positive charge from one point to the other. Definition. According to definition, what is it? Work done to take a unit positive charge from one point to the other. What is it? Work done to take a charge from one point to the other. Unit positive charge in a one point in the other point work done. Other than work done. Potential difference. Correct. Potential difference. What a potential difference and by the one point this, one point this. Okay. What is the potential difference? Equipotential and the potential difference and
zero.
Zero. Potential difference is zero. So what is the work done? Work done to move a charge from one point to the other is zero. So what is the work done?
Zero.
Zero work done. That's our property. Work done to take a charge from one point to the other on an equipotential surface is zero. Because potential work done to take a unit positive charge from one point to the other means that is the potential difference. If there is no potential difference, work done to take a unit charge from one point to the other is zero. So that is an important property. So show that work done to take a charge on an equipotential surface is zero. And another property is these field lines are perpendicular to the equipotential surface. Work done. What is the formula, children? Work done F dot dr. Work done dw equal to F dot dr. F equal to Q0 E. So if E is constant, we can take F dot dr. I will show the equation. Okay, you cannot remember all those things. I will show this equation. equation I'll show you. So work done to take a charge for an equipotential surface is 0. Right, not moving. Let me close it. Not moving. Raining because of that. The tissue. Let us wait for some. അപ്പോൾ ഇത് തന്നെ വെച്ച് നമുക്ക് വർക്ക് ചെയ്യാം, എക്സ്പ്ലെയിൻ ചെയ്യാൻ നോക്കാം എന്നുള്ളത്. അതും ശരി. സ്ഥലമുണ്ടായിരിക്കാം. അപ്പോൾ നമുക്ക് പറഞ്ഞ കാര്യങ്ങൾ പറയാം. ഓക്കെ, അത് ശരി. ഓക്കെ, നമുക്ക് പേജ് എടുക്കാം. Page also gone. No problem. We can take equipotential surface, page number 11. Due to rain, it may be. Okay. For a sphere, see, for a point charge, what is the shape of the equipotential surface? They are concentric spheres. And the field lines are perpendicular to equipotential surfaces. At a distance r1, potential is, yes?
Can you Pavitra?
Pavitra is not here. But see, it is not showing here. Let me see here. It is. Okay. Yes. Pavitra and Jnana Prakasham gone out. Okay. So here, see, point charge is marked here. Around that, we have drawn concentric spheres. And at a distance r1, the potential is V1. At a distance r2, potential is V2. At a distance r3, potential is V3. And we know as distance increases, potential decreases. So V1 will be having greatest potential. V1 greater than V2, greater than V3. Like that. You have to mark. For a point charge, this is the case. Clear, children? This one understood?
Teacher, ഇതൊന്നും explain ചെയ്തതാണ്.
ചെയ്തതാണ്, പക്ഷേ ചോദിക്കുമ്പോൾ കിട്ടണില്ല, ഇക്വേഷനും കിട്ടണില്ല, ഒന്നും കിട്ടണില്ല. That is the പ്രശ്നം. ഓക്കെ, പഠിച്ചു തന്നാലേ കിട്ടുള്ളൂ. നോക്കട്ടെ ചോദിച്ചു നോക്കട്ടെ. ഈ പോയിന്റ്സ് എക്സ്പ്ലെയിൻ ചെയ്യണം കണ്ടോ. See here, if parallel lines you can see, that is uniform field. In a uniform field, what is equipotential surface? They are parallel planes. That parallel planes you have to draw. That will be perpendicular to the field line. Always that is another property, children. Equipotential surfaces are perpendicular to the field line. Very important property. Equipotential surfaces are perpendicular to field line. Okay. Then equipotential surface for a pair of similar point charges. You have to draw this figure, which is a 1 mark question. Draw the equipotential surface for a system of two equal charges. ഈ പ്രോപ്പർട്ടീസ് ആണ് നമുക്ക് പഠിക്കാനുള്ളത് കേട്ടോ. വരയ്ക്കാനുള്ളത് നിങ്ങൾ പഠിച്ചോളൂ. So no work is done in moving a test charge over an equipotential surface. That is what I explained just now. This is an equipotential surface. At every point, the potential is same. A and B potential is same. So work done to take a unit positive charge from A to B, that is potential difference VB minus VA equal to WAB by Q0. As VB equal to VA, we have to write left side becomes 0. VB equal to VA becomes 0. So WAB by Q0 equals 0. That means Q0 cannot be 0. Then what can be 0? WAB. Work done to take a charge from one point to the other is 0. Clear this point, children? One mark question is it asked. What is no work is done. What is the work done to take a charge, unit positive charge on an equipotential surface? Why no answer? Aditya understood?
Yes, teacher.
Okay. Next, the electric line of force are always perpendicular to the equipotential. That is what I told. This also ask as 1 mark question. Electric lines of force are always perpendicular to each other. How can you say that they are perpendicular to each other? Suppose this is the equipotential surface and we have drawn the field line perpendicular to that. We know the work done is also equal to F dot dr, F equal to Q0 E dot dr, and that is work done is 0. Work done to move a charge on an equipotential surface is 0. So we take work done equal to 0. When it be 0, E dot dr, E dr cos theta. When cos theta becomes 0, for which angle, children? Cos theta becomes 0 for which angle? Which angle cos theta is 0? 90 degree. 90 degree. So angle between E and dr becomes 90. That's why work done is 0. The explanation is continuation of this explanation. Here we tell work done to take a charge on an equipotential surface is 0. Understand? And here as work done is 0, then F dot dr, F equal to Q0 E. Work done is F dot dr. F equal to Q0 E dot dr equal to 0. Then that it happens only when E and D are perpendicular. That means angle between E, electric field, and dr, distance moved on the surface. E and dr is the distance moved over the surface. So that if they are perpendicular, then only the work done becomes 0. So E is perpendicular to R. Such question usually ask 1 mark or 2 mark question. Second point clear, children? Aparna, second point clear?
Yes.
Aparna, explain. How will you explain? Electric field is perpendicular to the equipotential surface. How will you explain, Aparna?
Teacher, that when work is equal to 0, the angle will be 90 degree.
90 degree.
So
E dot dr. F work done is, what is the formula for work done? F dot dr. F equal to, what is F?
Q0
E dot dr equal to 0. That happens only when theta, angle between E and dr is 90 degree. Okay. Then next one, equipotential surfaces indicate the region of strong and weak field. That means equipotential surfaces are close. What is the meaning? If the equipotential surfaces are very close, what is the meaning, children? The field is?
It is strong.
Strong. Yes, field is very strong. Equipotential surfaces indicate the region of strong or weak field. If they are far apart, we can tell the field is very weak. If they are close each other, we can tell they are strong. Electric field is strong there. If we go from this equation, you can show that E equal to minus dV by dr. We have studied relation between electric field and potential. E is equal to very important relation, very important relation. Electric field E equal to minus dV by dr, or dr, distance of separation, dr equal to minus dV by E, and dr is inversely proportional to electric field. Separation between the surfaces, separation between the surfaces. If it is more, electric field is less. If the separation is less, electric field is more. Is inversely proportional. So with this formula, using this, you can show that. If E is strong, dr will be small. That is, separation of equipotential surfaces will be smaller. Thus, equipotential surfaces are closer in the region of stronger electric field. On the other hand, equipotential surfaces are farther apart in the region of weak electric field. Clear that point? Equipotential surfaces are far when the electric field is
Weak.
Yes, correct. We can move. Two equipotential surfaces never intersect each other. So as the property of field lines we have studied, two electric field lines never intersect each other because at the point of intersection there will be
Two
directions of electric field, which is not possible. Just like that, here also we can show that when they cross each other, two equipotential surfaces cross each other, at the meeting point, there will be two directions of electric field, which will not be possible. At the point of intersection of the two equipotential surfaces, there will be two directions of electric field. There will be two potential at this point. There will be two potential at the point. For a charge, is it possible to have two potential at the same time? No. So it will have only one potential. So hence it is not possible. So we have studied the properties of equipotential surfaces. Very important, children. You have to study very well. Okay. Next is electrostatic potential energy of a system of point charge. Why a system of point charge? So usually when a charge possesses energy, the work done, potential energy means the work done to bring a charge from infinity to that point in the electric field. Then work done to take a charge from infinity to that point. Potential energy of the system. Here, system means two charges are there. System, not a single charge. Two charges are there. Potential energy, see, electrostatic potential energy of a system of point charges. Like a number of charges it can be 1, 2 or 3 or 4, like that. Number of charges it can have. Potential energy. So, potential energy for a system of two charges, that is what we are going to derive now. Potential energy for a system of two charges. Two charges. We have, in order to keep them at particular distance apart, we have to do work. Let us see how it happens. I will explain. First formula written, that's all. Next explanation. Electric potential energy of a system of 2-point charge. That is our aim, to find the potential energy of a system of 2-point charges. Okay. So first consider both the charges are at infinity. First you have to consider both the charges are at infinity. At infinity, what is the potential, children? Potential at infinity, 0. Potential at infinity is 0. So, first initially both the charges are at infinity. First we brought the charge Q1 and kept at P1, children. First, what is done? Initially, both the charges were at you have to complete infinity. Okay. Then next step, we brought the charge Q1 to the point P. What is the work done? Or do we need to do any work to bring the charge from infinity potentially 0? What is the work done to take a charge from infinity to the point P? Here there is no field. Here there is no other charge. So no electrostatic force is here exerting on us. We are bringing the charge. See, we are having a charge with us and bringing the charge Q1 and kept it here. No force is exerting a force upon us opposite to our motion. We are bringing the charge. But no external force is acting. Now outside electric force is not there. So work done to bring a charge from infinity to the point P is, tell, what is the work done? 0. Because no electrostatic force is exerting opposite to the work done by us. So work done to bring the charge Q1 from infinity to the point P, that is W1, that is equal to 0. But you know, to bring that, already now the charge Q1 is kept here. Now we are bringing the another charge Q2. Then only it becomes a system. So we bring another charge Q2 from infinity to another point at a distance R12. Suppose it is R12 is the distance between these two charges. So in order to bring another charge from infinity and to keep it here, we have to do work. Why, children? Why we have to do work? First charge. Why? Why?
Because of the force exerted by Q1.
Yes, correct answer. Because this charge, positive charge, we are bringing another positive charge. So, which will repel. This charge will have electric field around it. This charge will have potential around it. So, in order to bring another charge to its field, we have to do work. So, that work done to bring the charge Q2 from infinity to the point P2. Infinity to the point P2 equal to potential into charge. QV, potential, work done is equal to Q into V. That is the formula. Work done is equal to work done per charge, unit positive charge, that is potential. So, work done equal to potential into charge. So, potential at this point is 1 by V1, that is equal to 1 by 4 pi epsilon 0 Q1 by R12. Potential into charge means V1 into Q2. V1 into Q2. Here the potential is V1. We are bringing the charge Q2. So potential at this point into charge will give the work done. So W2 equal to 1 by 4 pi epsilon 0 Q1 by R12 R12 into Q2. R12 into Q2. So we got 1 by 4 pi epsilon 0 Q1 Q2 by R12. So now first work done to bring the charge to the point P1, that is equal to 0. Next, the work done to bring the charge Q2 from infinity to the point P2, we have calculated W2 equal to 1 by 4 pi epsilon 0 Q1 Q2 by R12. So total work done will be both the work you have to add W1 plus W2, that is the total work done. That will be stored in the charge as potential energy. So what we get, same thing we are getting, because first work done is 0. So what is the work done now? 1 by 4 pi epsilon 0 Q1 Q2 by R12. So see, initially only you will have difficulty in studying this. Later you will be knowing when a charge is kept here, the potential at a distance R12 is 1 by 4 pi epsilon 0 Q charge by that distance R12. Then work done is equal to Q into V, only 2 steps. Potential at this point due to this charge, first we write. And work done to bring the charge Q2, that will be potential into this charge. So into Q2. So that is the answer. So this is the final answer. Clear, children? Understood this one? How to derive?
Yes, ma'am.
Okay. All these you have to write and study. That is needed. Next, 3 charges you can see. 3 charges. Now, problems come from this part. Very important. So 3 charges. First one charge from infinity, we brought the charge to this point. Next we brought the charge Q2. Then we already calculated when 2 charges, in order to keep a distance R1, 2 separation between them, we have to do work, and that we have already calculated. 1 by 4 pi epsilon 0 Q1 Q2 by R1 2, that we have calculated. And now we have 2 charges, and both the charge will produce a potential at this point. What is the potential due to this charge, children? At this P3, what is the potential due to this charge? 1 by 4 pi epsilon 0? Tell, Maharonisa.
Yes, teacher.
What is the potential at this point due to this charge?
1 by 4 epsilon 0 Q1 Q2
Q1 by what is the
1
distance?
R1
R1 3. What is the potential at this point due to this charge Q2? Mitra, potential at this point due to this charge?
1 by 4 pi epsilon 0 Q1
Potential at this point due to this charge.
1 by 4 pi epsilon 0 Q2 by R23.
R23, correct. But both will have potential. The sum of potential we have to find out. Both will have potential, and we have to find the sum of the potential. You see, potential at P3 due to the charges Q1 and Q2. See, we are adding both the potentials. Common factor is taken outside, and Q1 by R13 plus Q2 by R23. Therefore, work done. Now we got the potential. Now how will you calculate the work done to bring a charge Q3 from infinity to that point? That potential into, tell, work done, that potential into
Charge.
Correct. Which is the charge here? Which is the charge we are bringing? Q3. We are bringing Q3. Potential we already calculated. We are bringing the charge Q3. So into that we have to do. So the work done to bring